Recording in progress.
Okay, so this unit is about sketching graphs of polynomial functions. And what we're going to do is we're going to kind of just read certain paragraphs. Like I'll kind of, there's an activity, but we'll kind of avoid that. I'll just do a lesson instead with you guys, just so we kind of get this done quickly, and then we can go outside and enjoy the beautiful weather.
We go outside?
I said that like 10 minutes ago. Geez, I mean, she's just not paying attention. Exactly. Yeah, I know you do. Okay. Anyway, let me read this paragraph first, guys. So quiet down, please. So in previous course and chapters, guys, quiet, please. You learned how to graph many types of functions, including lines and parabolas. So you guys have done that, linear functions, quadratic functions. So today we're going to focus on some a little more complicated polynomial equations. Polynomial means more than one term. Poly, right? More than one. And these are going to be degrees of 3 or greater. Now, linear functions and quadratic functions are polynomials as well, but we're going to go beyond that, degree 3 or higher. So just as quadratic polynomial equations can be written in standard factor form, likewise, the polynomial equations can be written in standard or factor form. So the first equation, see, y equals x to the 4 minus 4x cubed minus 3x squared plus 10x plus 8. Okay, that's 5 terms. That's standard form. We call it standard form because you're listing each term individually, and also we're going in descending order. Taking the highest exponent and going down order until we get to the constant. The constant one that doesn't have x or a variable, we hate. Or if you have factor form, now not all polynomials could be factor. In this case, this one is great. But this factor form, we have the parentheses, and sometimes some of the factors are repeated, like the raised to the second or third power, fourth power. That could happen as well. So let's talk about this next example. The Math America Land Carnival Company has decided to build a new roller coaster. There's a roller coaster. So kind of like with Trig, we did like the Ferris wheel. This is now a roller coaster. Has a special feature. Part of the ride will be underground, just like the Ferris wheel. Designers will use a polynomial function to describe different pieces of the track. So this is the track, right? Sure. And it's going to be contours, or the way this path is defined. There's going to be some sort of equation. Some sort of equation is going to define that path. Okay. So part of the design shown to the right, your task is to guess a possible equation, throw it on the track, and test it on your graphing calculator. To help get an idea of what to try, start by checking the graphs of the equations given below. Think about how the graphs are the same, how they are different. So I'm going to punch each of these 3 equations into Desmos, okay? And we're just going to take a look. We're going to see which one it looks like. And then we're going to also investigate a little bit as well. So let's see here. And let me get the notes in front of me so I don't have to go back and forth. Okay. So we have y equals, guys, please be quiet. Thank you. Okay, so and that's raised to, no, yeah. So it's not going to be that one. That's for sure. That's a quadratic equation. So parabola. It's not going to be that one. I know that. Let's try this one here. Maybe it's this one. Okay, maybe. But it goes up. We don't want it to go up like that. So let's try the third one. X minus 2, and x minus 3. Probably not that one either. So neither of these 3 are looking very good for us, right? So we have to, so then it says here, and think about how they're all the same and different. Well, I do see that the second and third ones kind of look pretty close, right? I do see a bounce at 2 for the blue curve, but I see it pass through for the green curve. The first curve is pretty much different compared to the other 2, but it does pass through at 2. I do see that, and at 0. So all of them have 0 as an x-intercept, and 2 as an x-intercept. That's how all of them are same. 1 is very different than 2 and 3 because 1's a parabola. The other 2 are a little more curvy, like they go up, then down, then up. So that's interesting. If you were to expand second and third equations, let's just start with the third one. If you were to distribute a FOIL, what do you think would be the highest exponent if you were to expand this fully? Higher than that. Exponent power. Cubed. And likewise with this one. If you do x minus 2 squared, you get x squared, and distribute that to get x cubed. So that's what happens there. Okay. So your task, I mean, I'll do this with you guys. Your task is to Use information you found by graphing the above equation to help you make guesses about the equation that would produce a graph of the roller coaster. Once you've found a graph that has a shape closest to one, try zooming in or changing the viewing window. See details better. Keep track of what you tried and the equation you find that fit most accurate. So this is supposed to be an activity that you guys are supposed to, by trial and error. But I'm gonna have you guys kind of just tell me what I should do. So I don't like the first one. I'll get rid of that one. I kind of like the third one. Why do you think I like this one? Because when I compare it to the notes again, right? What are the x-intercepts of this roller coaster? Where's it crossing the x-axis? 0, 2, and 3, right? So it's crossing at 0, 2, and 3. And it's bouncing at 2, right? It bounces at 2, but crosses at 0 and 3. So that's interesting. Okay. So this is the part where I really need you guys to think. Think hard here. And actually, let me put that back to the other equation again, the second one. So notice that when I had the x minus 2 squared, notice that the purple curve bounced, right, at 2, but the green curve passes at 2. So it's interesting. We're noticing that if you see it bounce here, it's probably because the factor has a 2 next to it. For example, what if I were to, let me turn this one off and turn this one back on again. What if I were to raise that to the second power? Do you see it bounce? Where do you see it bounce? At what x-intercept do you see it bounce? Okay, right now we don't see any bounces, right? We don't see the graph bouncing off the x-axis. But when I did this, do I see a bounce? Where? At what x coordinate does the graph bounce off the x-axis or deflect? No, it's passing through it too, guys. Bounce. It deflects. No. Okay. I'm gonna travel. I'm gonna hit the x-axis. Do I pass the x-axis or do I bounce off? Thank you. Okay. Maybe you guys didn't understand what I meant by bounce. Okay. Now I hit 2. Do I bounce off 2 or do I pass through 2? Pass. And then when I hit 3, do I bounce off 3 or pass 3? Pass. There we go. Good. Okay. So most likely, I might need to bounce off 2, right? Because the graph on the notes shows a bounce at 2. So I'm going to raise this to the second power. Now I've got something that looks pretty good, right? Now this looks pretty close to what I see in the notes. So this is more the discovery part. Realizing that when you see something raised to the second power, we're seeing a bounce. If you don't see something raised to the second power, like if it's just x or x minus 3, it's going to pass through. There's actually a bigger reason why that's happening. We're going to explore that next week. But for now, let's go to the next page of the notes. Oh, you okay? Oh, okay. So I'm going to cheer. Oh, what is that? Okay.
Oh, that over here. It's like landing on my arm.
Okay, guys, if you guys want to go outside, it's up to you. I mean, let's let's focus, guys. All right. Now, here are 8 different equations. I'm not going to do all 8 of these because that's too much. But I think what would be interesting to look at would be this one right here. This one right here. Probably this one right here. I think that should be sufficient. Yeah, we'll do that. Those are 3 good ones to look at. So what we want to do is we want to I'm not gonna make a table, but let's state the x and y intercepts. Let's figure out the turning points and also how the ends of the graph behave. So what I'm going to do is I'm going to make some comments about each graph here.
Yeah.
So we're going to make some comments about the x-intercept, the y-intercept, the arrows, which actually I call end behavior. And probably the turning points. Okay, so let's look at the first equation. x minus 2, x plus 5 raised to 6. So P1x. Let me close these. Get rid of that. Get rid of that. Let me move this over here. Perfect. Okay. So x minus 2, x plus 5 raised to the second power. Okay. So look at this graph. So turning points. This is called a turning point. That's called a turning point. So I have two turning points, right? Because it goes up, down, then back up again. So basically any peaks or valleys is what you want to consider to be a turning point. In terms of x-intercepts, it looks like it's at -5 and 2. The y-intercept is really, really negative. Looks like it's at -50. That's easy, just plug in 0 for x anyway. And the arrows go like this. So the graph is kind of doing like this, right? So the arrows go like that. And these are things we'll investigate in more detail next week. But right now we're just observing. We're just making observations. And these are the 4 observations I want you to make. Turning points, arrows, x-intercept, y-intercept. So that's P1x. Let's do P5x. So let me erase this stuff here. So you want to make notes somewhere on your notes. P5x. Let me erase this as well. All right. So we got ourselves -0.1 x and x plus 4 raised to the third power. Okay. So what do you notice about the arrows now? Are they both pointing up, both pointing down? Both pointing down, totally. Yeah. It's kind of like that, right? So the graph is doing something kind of like this here. Some really kind of funky like that. And I see really just one turning point. Even though it does flatten out, it's not really a turning point. Turning point means you change from going up to down. Think of like a roller coaster, right? When you start seeing a change in like whether you're going up or down. So I see just one turning point here. The x-intercepts look like it's -4 and 0. The y-intercept is 0, and the arrows go like this. Okay. By the way, domain and range. We didn't do that for the previous problem. I'm just going to tell you right now, the domain and range for any polynomial function is always all real numbers. That's always true. There's no restrictions at all for any polynomial function. It's always all real numbers. So we'll write like this, because we're starting to get in the habit of doing interval notation. So that's true for any polynomial function. True. Geez. Just cannot write. True for all polynomial functions. So, yep. Okay. We're good? All right. Oh, why did I delete that? That was dumb. Here we go. Let me just delete some of these things here. Finally, P at x. Okay. So we have x to the 4. Let me erase this. So again, polynomial functions, all true. That domain range is all real numbers. Okay. Now this one's not factor, so x raised to the 4 power minus 4x raised to the 3 power. minus 3x raised to the second power plus 10x plus 8. Okay, so it looks like that. How are the arrows pointing here, guys? Both up, okay. So the graph is kind of doing something kind of funky like this. How many turning points does this have? 1, 2, 3. See how like it's a roller coaster, right? It goes down, back up. So basically how many peaks or valleys or mins or maxes we got? Those are called turning points. Again, these are all things we're going to explore in more detail next week. There's no vertex actually. We don't call these a vertex, but we call it high or low. Yeah, because it's not a parabola exactly. I mean, it's not a parabola at all. The x-intercepts look like it's going to be, if I zoom in, okay, those come out really nice. So you have 3 x-intercepts, -1, 2, and 4. The y-intercept, that came out really nice. That's 8. By the way, the y-intercept's actually pretty easy to figure out. Just that last number, right? If you plug in 0 for x, all the other terms vanish. And what is an x? Sorry, what is a y-intercept? When x is 0, when you cross the y-axis. When x is 0, you only get 8. And both arrows point up. Okay, so these are all just observations we're making. Actually, we're almost done. So let's look at page 3, and then there's a bunch of terminology right below, and then homework is on the page after, and then we're done.
U1 factor.
Okay. And by the way, just this unit is about polynomial functions, something called complex numbers. This is a list of the topics here. Might not make too much sense. I won't go over all those things right now. Let me just close this. All right, so let's look at page 3, guys. Okay, can we factor these? And the answer is yes. Okay, when you factor, and by the way, factoring is essential for this unit. If you're struggling with factoring, come see me during office hours next week. I'll help you with it. Because it's one of those, just like math in general, right? Like, you build upon previous knowledge, right? This is previous knowledge that we need to be very sound with. Factoring is something that was done often in middle school. We try to reinforce in geometry. We did it in fall semester. So it's got to be more natural now. If it's not, it's okay. Just talk about it. I'll help you. So you usually want to find what we call a GCF. Do you guys know what GCF stands for? Thank you, Monty. Yes, greatest common factor. And thank you for those who chimed in. So among all terms for the first equation, x cubed, -21x squared, plus 20x, among those 3 terms, what's common among all 3? X. Let's take it out. You have x squared minus 21x plus 20. Now, some people have like all these different techniques of factoring, but if you could just see it, more power to you. Fortunately, this is a pretty easy one. X and x. And what 2 numbers multiply 20 after -21? -1 and -20. Perfect. Good. Yep. Okay. And then this one here, y equals, now what's the GCF here? X squared. Good. X squared is common to both, so you pull it out. And we're not out of the woods yet because it's not totally complete. Whenever you have something with x squared, you want to check to see if you can break it down further, just like in the previous equation with x squared minus 21x plus 20. X squared minus 9, when you have 2 terms and a minus in the middle, typically you'll have the opportunity to do difference of 2 squares, meaning the first and last terms are perfect squares and can be broken down further. X squared 9 are perfect squares. How would I break this down further? And x plus 3, yeah. Because if you were to FOIL, remember, FOIL is the opposite of factoring. Some people say, oh, I FOILed this. Like the first and second step, people call this FOIL. No. FOIL is when you go from the second to the first step, when you make it expanded. When you break it down into its factors, there's a lot of factoring first. But FOIL is the opposite of factoring. And instead of FOIL, check to make sure you did it right. But FOIL x times 2x plus 3, I'll get back to x squared minus 9. So you should always get back to the same thing. So this is helpful because now I can find the x-intercepts, right? So this is a skill that we need to be very good with in order to move forward with polynomial functions, because we're going to be also solving these down the road and maybe doing some modeling. We'll see. I have to look at the notes. Some terminology, very important. Coefficients are the numbers in front of each variable. Constant is a last term, right? Bi means two. Poly means many. But polynomial could also be one term too. We call like a single term polynomial if we want. Very important, a polynomial function cannot have fraction exponents. So very important, guys. So the exponent will always be a whole number. If it's a fraction or negative number, forget about it. The coefficient can be a real number. That's fine. We are going to talk about non-real numbers, imaginary numbers later on. Have we had that discussion? I don't remember about imaginary numbers. I don't remember. Okay, I have to look that. Well, anyway, I know we talked about in this unit. The ones that were says are not polynomials, like 2 to the x power. Your exponent can't be an x. The x is only the base. And again, you can't have fractions like 1 over x. I mean, yes, you have fractions for your coefficients, but you can't have x as part of a fraction, or you can't have radicals. Remember, 1 over x squared minus 2 is a rational expression. I think we've talked about that. The degree is the highest exponent you see. And typically we want to write this in descending order, as I mentioned earlier. The last term that doesn't have an x is a constant. Sometimes you don't have constants. There's no constant for the first equation in the top left of this page here. If it's factored, you can determine the degree just by imagining if you were to expand it, what would happen. I see x plus 2 and x plus 5, or expand by x squared. So that's my highest exponent, so my degree is 2 for that one. I think that's kind of it for the all this information here. It's very rich in information, so I like it. So homework is gonna be pretty simple. Okay, so you do actually need to go. Okay, so I didn't. Great. Well, I'm gonna put this in Schoology. I'll try to actually make screenshots of these problems, but you do need to go to CPM textbook and do those problems in addition to these here. So this is not just the homework, just so you know. There's only 6 of the problems. There's still 6 other problems: 8-7, 8-8, 8-9, 8-10, 8-11, 8-12. I'll make a screenshot of it. I'll put it in Schoology, so in case if you want to, if you don't want to access CPM textbook, you can just look there. But you do need to do those 6 problems in addition to these 6 here. These 6 here are just straight up factoring. So you're going to practice some factoring skills. If you want to do extra problems there. Some of this factoring you might have a little challenge with. That's okay. We'll talk about it on Monday. And that's pretty much it. So now the only thing I ask is that when you go outside, let's not disturb the classes. And because there's another Algebra 2 class, I'm going to probably get a little jealous. Try not to be too close to this. I try to go a little bit further towards Homer. Okay. All right. Yeah, once you guys take your backpacks, one class is out, you guys can get your next class.
Yeah.